Welcome to Brain Vision.
Okay, so this one is a long one. We have problem 780. We have a proton with mass m moves in one dimension. We have a potential energy function. We have positive constants a and b. Now, I might change those for alpha and beta throughout solving this problem because that's what's in the book. So just stick with me on that. And we have a proton that's released from rest at x sub 0. So first we need to show that this equation can be written as something else. So we need to show that we need to basically manipulate this equation, u of x, such that we get this down here. So we start off with u of x. That's equal to alpha over x squared minus beta over x. What I'm going to do is I'm going to multiply each term by the same thing. So it's going to be left with alpha over x naught squared, x naught squared over alpha. So this quantity is equal to 1. I'm going to multiply that by each of them. So we have alpha over x squared. I'm going to do this, write the same first two terms. Minus alpha over x naught squared, x naught squared over alpha, and then beta over x. And then I can pull out the term in front. So we have x over x naught squared. That's the first term we need here. And then you can do some simplification. So this will cancel out. And then we have what we can substitute what beta is equal to. So beta is equal to alpha over x naught. And I probably should have written that a different color. But then we can say, okay, that's gone, that's gone, that's gone, 1 power of that is gone. And what we are left with is our x naught squared over x squared minus, we took this out, so we're left with x naught over x. So that's a different term. That's what b cancels out to b. So I wrote that in a different color underneath. Okay, so that's part A. We rewrote it. Okay, so now we calculate x sub 0, u of x sub 0, and we thereby locate the point on the graph after we graph it. So if you graph it, generally, like put in alpha and beta equal to 1, you're going to come up with a shape of graph that looks like this. And it looks a little more smoother down there. It's not as jagged at the bottom, but just to show emphasis, it comes down from above the axis, and it crosses through the axis at a specific point, and then it rises up towards the axis again. And you would get this general shape for any positive constant you put in there. I just put in 1 just to graph it on a calculator on Wolfram Alpha, and this is what it looks like. So now we're supposed to calculate u of x sub 0. So u of x sub 0 where x sub 0 is again alpha over beta. So that's alpha over alpha squared over beta squared. Actually, I can do this much easier on myself. So alpha over x squared. You can substitute in x is equal to x naught squared. Minus x naught over x naught. And that's 1 minus 1. That's 0. This whole term is 0. And that makes this, that means that at x sub 0, that is when it is equal to 0. So this point is x0. Okay. B, calculate Vx, the speed of the proton as a function of position. Okay, so when since x sub 0 is when where it's released, the proton is released from rest right here. That means that at that point we have zero potential. We have zero kinetic energy, zero potential energy, and then we're supposed to calculate Vx, v sub the function of x for velocity, and then we're supposed to calculate what happens for the velocity throughout this motion. So what I'm going to initially start out is write down our conservation of energy formula. We have kx, that's the kinetic energy, plus u of x. And at this point here, we've determined that since it's released from rest and the potential energy is 0 there, that's where the intercept is, that's equal to 0. We can substitute in what k of x is equal to in terms of v of x, 1/2 m v of x squared plus u of x is equal to 0. Okay, and then this can be solved for v of x is equal to -2 u of x divided by m quantity under the square root. And then you can substitute in what u of x is, whatever nasty formula you'd like to put underneath the radical. Okay? And then we're supposed to graph it. I'll go to a new page. But essentially, what we're going to get is we have v of x. And again, it's going to start from rest at our point x0. And it's going to look similar to a square root function that you get normally. It's going to go up and down. I should give myself a little more space here. It's going to reach some maximum that's going to correspond to the point where this is a minimum potential energy is maximum kinetic energy, which is a maximum velocity. It's going to correspond to some point right there, and it's going to trail down as the potential energy approaches the axis again. Okay, so what was the next part? For what value of speed of x is the speed of proton maximum? Okay, so I can write down what I've already described before. We have v max at some point of x is going to correspond to when we have potential energy at a minimum at the same value of x. So in order to find the minimum value, that tells us we need to do a derivative. So we have d over dx of u min, actually I shouldn't write min, of u x is equal to 0. Okay, so we can write down what that is, d over dx. And I'm going to rewrite it so it's better for me to see what I'm doing. Minus beta x -1. And that's going to be equal to, bring down the power, -2 alpha x, reduce the power, plus beta x -2. -1 times the -1 we brought down is a positive right there. That's going to be 0. Okay, then we can solve this. Multiply each term by x to the third, and then actually just x squared. And we're left with 2 alpha over x plus beta equals 0. And then you get x is equal to 2 alpha over beta. And surprisingly, or maybe not, this is equal to 2x naught. So apparently, this point here is 2x naught when it's at a maximum. Okay, so that's interesting. Let's see what's next. What's the value of maximum speed? Did we determine that? No, we just determined the position where x is. So we need to determine what the actual maximum speed is. So we can go back to our equation for velocity. So the 2x naught, and that was equal to -2 over m u of 2x naught under the square root. Now we can substitute in what u of x is, and I don't want to write down all again. So -2 over m. The constant out front was alpha over x naught squared, and then we get a quantity in brackets that was -1. That is -1 over 4, and it's going to be equal to alpha over 2m x naught squared under the radical. Okay, so that's what that value is. Let's see what's next. What is the value of maximum speed? What is the force on the proton at that point? At the point in part C. Okay, so let's solve that. We know that we have the equation F of the force at that x is equal to -d over dx u of x. So F at 2x naught, that point up there at the peak, is equal to that derivative again at that 2x naught. I'm just going to break down what that is. So we have negative. We already have what the derivative is from before, so I'm just going to copy this, but replace the x with our 2x naught. So we're going to have 2 alpha, 2x naught, quantity -3 plus beta, quantity 2x naught, -2, and all that times -1 at the front. Okay, and that will get simplified down to alpha over 4 x naught 3 minus beta over 4 x naught squared. And then this is going to simplify, is going to be it's going to be, when we substitute in x not equal to alpha over beta, it's going to be equal to 0. And that's what we expect. If we have our minimum potential energy, that's where it's going to be. It's going to have the force could be 0 because there's the slope on either side. It's positive. It's negative on the left-hand side, so it's going to push it this way. Positive on the right-hand side is going to push it this way, which means that at the center there's going to be no force. Okay, so what's next? Let the proton be released instead at x sub 1 equal to 3 alpha over beta. Locate where that point is on the graph. Okay, go to my next page of notes. I'm going to go to a new page. So what we have here again is we have x comes down. Okay, so this is x0. That's this was our point of 2x0, 2x0, and at some point here we have 3x0. That's where the particle is going to start. So we can write down we need to find what that value is. So x1 is equal to u x3 x0, and it's going to be equal to alpha over x naught squared. And we can again write down what this is. So x naught over 3x naught, quantity squared, minus x naught over 3x naught. And then that leads us to alpha over x naught squared, -2 over 9. Okay, what was the next question? Calculate Vx and give a qualitative description of the motion. Okay, so we're going to do the same thing as before when we had the conservation energy written out. We have 1/2 m Vx squared plus u of x. At this point, however, we've already determined what that value is at that point, x1 or 3x0. That's going to give us a potential energy equal to this. So alpha over x naught squared, -2/9. And then we can solve for Vx. So it's just going to be the same thing as before, but with the constant there in brackets. So it's going to lead us to square root 2/m bracket alpha over x naught squared -2/9 minus u of x. So it looks a little nastier than before, but that's because it's not starting at a point that's where we have 0 total energy. Okay, so then what's the next one? F. Actually, we need to give a qualitative description. So if we start here, it's closer to the axis than at the bottom, which means that when we look at the force that is acting on this point, it's going to push our particle to the left. It's going to hit some point here. It's going to reach some point where there's not enough energy to move up this slope, so it's going to go back and forth. Okay, reach release point, where maximum minimum values of x reach during the motion. Okay, so let's start with the release point x sub 0. So this is problem F, and x is equal to x sub 0. We have u of x is equal to 0. So that's 1, that's the start point, that's the minimum value. It can't go to the left of that. Well, let's find the maximum value. And so because of conservation energy, it's going to have a velocity that's going to be positive as it moves to the right. But at some point, it's going to possibly reach the axis, which is its maximum value, and go back. So let's see if there is a point like that. So that means we have equal to alpha over x naught squared, x naught over x naught, x squared. Sorry, I'm saying x and x naught, that's the same thing, but they're not. X naught over x. Okay, we need to find out if there's any other place than 0. X equals x naught, where this equals 0. So we can multiply this both sides, divide both sides by this. So 0 is equal to x naught over x squared minus x naught over x. Is there any place where this is equal to 0 other than x naught? So we have 0, multiply both sides by x squared. So x naught squared minus x naught x. And then this divided by x naught, you get 0 equals x naught minus x. So there's only one place where where the potential energy is going to equal to 0, and that's going to be x equal to x naught, which means that there's no maximum value for this one right there. There's no maximum x. It goes on forever. But how about x equal to x1 equal to 3x naught? What is that? So we can write down what the potential energy for that is. I'm going to write down another page. U of 3x naught. You can substitute in what x is equal to, so you get alpha over 3 alpha over beta squared minus beta over 3 alpha over beta, and you're gonna get that equal to beta squared over alpha -2/9. Okay, so now this we're going to take this value and then that's going to be equal to our function of x for the potential energy. So that's the potential. So that's where it's going to be. So you can take beta squared over alpha minus 2 over 9. It's going to be equal to alpha over x squared minus beta over x. We can solve for x using quadratic formula. I don't want to go through that, but then you're going to have a result that is equal to two solutions. So quadratic formula gives two solutions. We have 3 alpha over beta and 3 alpha over 2 beta. And those are maximum values.